Hello children, welcome back. The portion we left the last time in the class was some application of moment of force. If you remember the part of the table and the movement displacing it from the hinge. So as the various examples are given in your book, I would like to show you certain illustration. So at the first one, just as a revise of the previous one, I would just like to show you the diagram as it is given over here. Yes, it is not in your textbook, but of course you can see over here that the person who is drawn, he is opening or trying to open or close the door from the door knob, which is at the extreme end almost or very far away from the hinge, and he is not using any center part or any other part of the door. In fact, what question can come normally based on this is, why are the why are the handles or the door knobs are kept away from the hinges? Answer should be same. That is, much lesser force will be required to open or close the door. We can consider at ourselves, no, it is not so. We can open the door by touching it on any of the point. It is not a problem. My dear, consider yourselves when you were 3 years old, 4 years old, child, right? So your strength will not be equivalent to that of the child. Or even there are aged persons like our grannies, grandpas. So it is also not possible for them to use a huge amount of force. Coming to our second example in the book. Now this example may not be very much available, especially nowadays in the urban areas. We can see it on the TV, especially the national TVs, and any other advertisements or pictures if you want. That is hand flour grinder. See the diagram over here below. I have marked it in such a way so that you can able to see it. Sorry, just give me a moment, please. I suppose now you can see a lady sitting with a hand flour grinder. Now, this hand flour grinder, they actually the handle which the lady is holding with the right hand is given at the extreme end, and the the grains are put from one end and the hand is rotated so that this grinder can work and give us the flour or the atta in Indian languages, which we mostly say. So this example is also there in your book. Of course, drawing the lady and drawing the hand flour grinder in the exam is not possible. You can illustrate as you wish, or if you want, you can illustrate with the diagram in your book, figure 1.3, where the moment of force and the application is clearly given. Now the third example, just below it, you see the bicycle wheel. I'm sure bicycle is seen by everyone, right? But in this case, the bicycle, whoever rides it mostly, I used to ride and can ride after a few days. So every time when we put the pressure on the pedal, I will give you a certain example of this, though not a bicycle. Still, I have another toy I managed somehow. Okay, so this is it. That is a rickshaw. Yes, a rickshaw. So it is quite similar in structure, because as you know that whenever a rickshaw puller drives it, he just gives the pressure on one side and it helps to displace it from the other side. Here the rickshaw puller is giving the force on the pedal, and this wheel is actually in front of him, but the whole of the rickshaw is being driven. See the diagram 1.7 in your book. Turning of a toothed wheel of bicycle. Over here, the foot pedal is fitted to an axle, and the pedal when ridden is helping the rear wheel also to drive. In the next page also there are certain examples. Whichever example you want you can give, but most of them, these are conceptual based question, might be 2 marks in the first part of you know very well the question. ICSE physics question is of 2 parts, part A and part B, just like the final exam paper of your class 9 came, same format. So these are actually 2 marks question, asking questions based on this. Explanation can be your own choice. A spanner used to tighten or loosen a nut is provided with a long handle. Now I don't have spanner at home, but I can show you with the example of this wire cutter. In no way it is similar. I will just like to demonstrate the physics behind it. See, in the wire cutter, where the handle is provided quite a long compared to the body top over here, this is the point where we put in the wire. I have put a broken pen just for the demo. I don't have any wire right now. Here, we normally put the pressure at this point, that is at the end point. See, you can see me holding it, and we try to twist and break the wires. Most of the electricians do carry this. If you want, you can check it. Most of the homes also have it for safety side or in case of small repairing works. But what will happen if I hold it over here? Number 1 problem, the wire is at this place. I can't displace it more. Number 2, when I have to displace it also, I got a sprain over here. That means much more force is required. In the other case, much easily a greater amount of displacement can happen, because the full of the handle is used, that means the full length, and the pressure is much less in this case applied by me, so the required force is also much less. The displacement is much more in case by applying less force. Moment same. A jack screw used to lift a heavy load. Now these type of things are very well used in factory areas or in the shipment in those cases. So in this case, a jack screw which is used, it is used to just lift any vehicle. Much less force is required in that case. We will now be concluding this portion and shifting to the next portion. From the above examples, we can conclude that the turning of a body about an axis depends not only on the magnitude, that means all these examples are considering the factors, that is the magnitude of the force and the same thing the perpendicular distance. Larger the perpendicular distance, less is the force required. Larger the force can be applied from small distance also. Applying force is a difficult factor, So we apply it from a large distance, like even at the door case or even at this wire cutter case. We will now be talking about couple. It is very easy to move a body when this pivot was loosened. See, it's a broken part, and that is why only I got the permission to take it out from the kitchen. If it would have been working, I would have been thrown out of the kitchen. So, very easy, right? What about this tap? Is this tap more powerful than me? I am applying the force continuously, it is not working. Or is this tap fixed? Is it a bad tap? No. There are some forces or some requirements for which we need to apply the forces simultaneously on both the sides. Example of that is this. Number 2 example, a very common one, your water bottle. One force not working. Working now. Perfectly working. So, the difference of another finger. Over here also, turning effect. Two equal and opposite parallel forces not acting along the same line form a couple. See the book page number 4, it is written in italics from the left paragraph to the right paragraph top. Please underline, a couple is always needed to produce a rotation in the case of these type of examples. In fact, yesterday it was not possible, but in case of this, this is the broken wheel part. So, in that case, if I want to produce a particular rotation, I need two parallel forces. Now, in this case, if second force which I can apply, I can take the help of the support of the ground, or in the case of steering wheel, I can hold it, or any driver can hold it and just rotate it in both the sides. There will be rotation around the pivot point or the axis of rotation. So, this will be known as couple. So, every time what we do is we measure or try to measure it and see ultimately that both side moments, that is clockwise moment, you remember yesterday or the last day of the class, that is we were talking about clockwise movement, that is the negative, and anti-clockwise moment, that is the positive. So, both these two moments has to balance each other. In this case, to balance the moment, we need to balance the force multiplied by the distance on both the sides. So, if I apply one force over here, another force over here of the same amount, difficult, and there is certain restrictions, not possible to move around this, possible to move. So, every time we need to check that whether the forces applied on both the side is same or not in case of the measurement. See in your book the diagram figure 1.14 for the couple action. Moment of force at end A and moment of force at end B. Their total sum will give the moment of couple. So, when this will be given, you can easily say that either of the force, not both the forces, they have not added up the forces. Check the equation of your book. Please, they have taken it common. So, force into distance but the full distance. In case it will not be the small distance from the axis, check the diagram, you will see D is written as the full of the diameter. That means the full size over here, here also it will be the full diameter, here also it will be the full diameter of the cap, not from the center pivoted point. So, this full diameter will be taken and any of the forces of any of the sides can be taken. That will give the total of the moment or couple. Our next topic is equilibrium. Now, why equilibrium is important? Because as you can see, partially, not fully, I have kept the book over here. What would have happened if the book would have been continuously in front of me? Very funny. During the exam time, you are trying to read it and it is running away. You are trying to read it and it is going down. You are trying to read it and it is going up. In the exam, your marks would also have been running. So, equilibrium is always a necessity. Question can come, Miss, there is no force, so there is equilibrium. Of course, you are not applying anything, you are not hitting the book, you are not pushing the book. That's why the book is at a static body, rigid body, and it is static and it is staying at the same time. Are you sure of this statement? Think again. Forces applied on the book. Number one, let me show you step by step. In this case, it will be easier to demonstrate if I use this box. Box kept at a certain place. So, in that case, if I take this, no force is acting. Are you sure? Let's see. Number one, every single person is being acted upon by gravity on the earth's surface. So, of course, the first force will be downwards, that is gravity. Second, as per Newton's third law, if you remember, action and reaction. Many a times you have punched each other. Oh, I am punching my friend, my best friend is also punching me. Action and reaction. And after that, a huge fight. So, this action and reaction is Newton's third law. When gravity is acting below, there is also one force acting. As you can see, I have kept my spectacles box on another small box over here. This box is giving a reaction force from the top, on the top, sorry. So, that means perpendicularly there will be two forces acting simultaneously, one below, that is in the gravity, one upwards, that is the reaction force. Both of the forces are actually balancing each other to create an equilibrium. Why I just put a pun on that? Because this is what I meant to show you. And even after the number of forces applied, I can see it to be exactly at the same place in which I placed it. So, as per the definition goes on, when a number of forces acting on the body produce no change in the state of rest or the state of motion, that time it is said to be in the state of equilibrium. Now, there is one word given in which there is more explanation is required, that is state of linear or rotational motion. Now, first let me complete the state of rest first. I will explain the state of motion after this, step by step. But in the definition, you have to write all of these words mentioned: linear or translational motion or rotational motion, and of course the state of rest. All should be clearly mentioned. In this case, I told you about the forces acting on it. There is a diagram in your book 1.15, you can see it, and in this there is also another example, a book lying on the table. This was a box lying on the table or two boxes lying on the table. All are similar type of examples. There is one example that is about the beam balance in horizontal position. You must have seen the grocery stores which are using the beam balance. That means they are holding the balance and they are using it, the two legs. This is of course not exactly representing, but it's just example to explain you certainly. Until and unless they exactly put 500 gram of something on the left side, on the right side if they put the 500 gram, the big iron hexagonal weight, that has the habit to come down. Excuse me. So, this can be done or taken as the example of equilibrium. Now, we will be coming for the next part, that is dynamic equilibrium. When we read the definition, there was a portion of motion, translational or rotational. So, when anything is in motion, when we study about that, the term comes as dynamics. So, this type of equilibrium which is already in motion but at similar type of motion is the dynamic equilibrium. When a body remains in the same state of motion, that is translational or rotational, under the influence of several forces, then it is said to be a dynamic equilibrium. Many days in the week or many days in the month, you have seen that it is raining, or if not regularly, but nowadays it is seen. Many are there who like to get wet in the rain. Many are actually pulled back by their guardians that don't get wet in the rain. But whatever be the quantity of the rain, it is not only one drop of water falling, but a good amount of water falling from the top and at the same velocity or at the same acceleration, it is better to say. Now, a raindrop reaches the earth's surface with a constant velocity. The weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction. Buoyancy, hopefully you remember, read it in the last class, and the friction. Now, when the raindrop is falling, there is a question, where is the friction? Air friction, atmosphere. Raindrop is not falling exactly from the rooftop, right? It is falling from quite a high distance. Where the clouds are. The clouds can be seen in stratosphere also. So, if I take the height of the troposphere only, from that height it is falling. So, it's not a very less height. In that case, even when after a certain long time, when it is reaching the ground for the full distance, it is maintaining its own velocity. When it reaches the ground, of course, just like any other body, it's when it touches the ground exactly, it's totally zero. The velocity becomes the rest velocity. But until and unless it reaches the ground, it maintains its full uniform velocity. It's not that I'm sitting in this position of the room when two cars are beside each other, when rain is falling from one to the other. It is not that this person is getting a huge amount and this person is getting a very small amount. Both of the persons waiting in the traffic jam is getting wet with the same velocity of the rain. So this is the basic concept of dynamic equilibrium. Another thing, if I explain as the rotational, yes, the same old broken thing, it is, if I keep on continuously moving it with certain force over here, which can continuously give it a force, you will see that its motion will be till this much, now stop. But when it was in motion, a good amount was in exact uniform motion until no one stopped it. Stop, motion, stop. So this can be also taken a good example of dynamic equilibrium. There are certain other examples given, a stone tied at the end, or the games like yo-yo, all these things, or an aeroplane traveling at a constant height in a cruise flight. It is known, when the aeroplane keeps its acceleration constant in a straight flight, it's known as the flight in cruise, C-R-U-I-S-E. Those who travel, or pertaining to the situation, those who used to travel, they already know all these. Missing travel, by the way. Conditions for equilibrium till whatever I have said. That means the resultant of all the forces, remember this, the gravity resultant and everything, the resultant of all the forces should be zero. Even if I apply forces from both the sides, since same fingers applied, so both side same force, equilibrium. The body did not displace. The algebraic sum of moments of all the forces acting on the body about the rotation should be zero. This is the case of the rotational motion. So the algebraic sum of the moments means, as you know, the clockwise and the anti-clockwise, both the things are denoted with different signs. So the clockwise and anti-clockwise moments with their sign, that is known as the algebraic sum, together should be 0. So these two conditions and actually give rise to the third thing, that is principle of moments. There are numericals based on this, which we will be doing very soon. Principle of moments, the sum of clockwise moments will be equal to sum of anti-clockwise moments. So this is actually the second factor also. Sum of clockwise algebraic moments should be 0, sum of clockwise moment and sum of anti-clockwise moment should be equal. This verification of principle of moments can be done by showing certain devices. Hope to see you soon for this again. Thank you.